All right, welcome to the second video of lecture 24. In this video, we're going to talk about what would happen if we tried to meet the entire world's energy demand using only solar panels or using only wind turbines. So let's start with solar. With solar, since we covered this at length in this class, I thought it'd be fun to, as a little exercise, try to guess how many solar panels we would need. There are published results out there of how many solar panels we would need to meet the world's demand, all of them to varying degrees of accuracy. We're going to try it ourselves. We're going to do it just kind of as a list of assumptions as we go. So first, we're going to assume that we have access to 1 day of storage. Essentially what we mean is we must be able to meet the energy demands of the world on the day that demand is created. So we don't necessarily have to produce that power in the moment. We'll say we have enough storage to generate, store, and push out that power when we need it in 1 day, but not enough storage so that the amount of power we generate will last several days, which means that we must have enough solar panels to power the Earth, well, to power humanity for 1 day. Okay. We're also then going to assume that we use power at a constant rate. So we consume energy at a constant rate. Of course, this isn't true for electricity, but when you throw in the fact that this is total energy we're talking about, not just electricity, right? So we need to power all of our vehicles, we need to heat our homes, we need to do everything with this power. And when we account for all of that, perhaps then we will have a relatively constant rate throughout the year. Well, I mean on a daily scale, a constant rate. So on February 14th, we'll need just as much power as in July or in October. Okay, and I'm sorry, I've been saying the word, I mean the United States. So if we take the energy consumption in the United States divide by 365, we get 75 billion kilowatt hours per day. So we must generate this much power in 1 day using solar power. Because we have to generate every day's worth of power that day, that means that we must generate in the middle of winter enough power with our solar panels in order to power the United States. So we're going to assume it is the middle of winter. Now, why would we do that? Because our solar potential is much smaller in the wintertime. So if we hope to truly power our country continuously, then we better have enough solar panels in order to power the country in winter. True, that means we will generate excess power in the summer to a significant amount. But unless we can figure out a way to store significant amounts of energy to power a country for months at a time in a reliable way for 6 months, then this is how it has to be. Okay, so we're going to assume it's the middle of winter. Let's take a look at the resource. So this is a pretty cool map right here. So this is the energy extraction potential. So the color corresponds to how many kilowatt hours we will extract per meter squared per day. So this is how much energy falls on a 1 meter by 1 meter square per day, and that flat plate is tilted south at latitude. All right. So if the solar panel is, say, here in Kansas, then that solar panel is tilted. This is now looking at it from the side. It's tilted at the latitude of where Kansas is. Okay, so our solar panels are all tilted. They're getting maximum output. And this is in January. If you look at the summer resource chart, it is significantly larger than this. But we are here in winter. Now you see the dark kind of brownish colors. These numbers are hard to see, correspond from anywhere from 2 to 3, very small. And then these darker reddish colors correspond to something like 7.5. And so we've got good potential here. Nothing in the north, including Ohio, and then decent in the south. So what I have done is I've said, all right, we're going to be generous, all right? We're making a very conservative assumption here. And what this means is we will actually need more solar panels than what we're predicting here. So we're going to assume 5 kilowatt hours. Sorry, my pen has not been behaving today. Per meter squared per day. 5. So that's honestly, when you look at this chart, I'd say that's too high for the entire country. I think 4, maybe 3.5 is more realistic, considering that we will build panels everywhere. We might try to concentrate them down here, but we don't want to have to port that power all the way to the East Coast. Okay, so we're assuming 5 kilowatt hours per meter squared per day. We're also going to assume a 20% efficiency. All right, when we do that, we actually get our answer. We know that we need 29,000 square miles of solar panels. If you take them, lay them out flat, you would need 29,000 square miles of solar panels. That is equivalent to the size of South Carolina. Right there. Imagine this, covered in solar panels. That's how many we would need to power this country. That's a lot of panels. It's 7.5 times 10 to the 10th meters squared. Assuming an average panel is 1.6 meters squared, that is a lot of panels. Okay, some things to mention is we didn't even consider some things that are going to make our answer, it's going to make our answer even worse. Okay, so first, not all panels in the United States are tilted. Right? Next time you drive past solar panels on someone's roof, sure, they're tilted, but are they tilted at latitude? Even worse, are they on the south-facing slope or on the eastern or the western-facing roof? If that's the case, we're going to get less power and we'll need more panels. Also, we haven't accounted for shading. We can't just put all these panels tilted right next to each other. We'll have to space them out. And as we space them out, we take up more land. In fact, that will require about double the amount of land, assuming all the panels are mounted on the ground. Okay, also we haven't thought about peak loads. Christmas time, any time that we expect the country to just use a ton of power all at once, are we going to be able to meet that demand unless we build even more panels? All right, if you really want to blow your mind, doing the same sort of analysis for the world, we find that we must cover the country of Libya with solar panels. Not to mention that demand in the world, remember we showed it's growing, and it's growing linearly. All right, what happens when you install massive solar? So if we put all of these panels, let's say we build a pretty decent sized solar farm in southern Utah, as has been proposed by Elon Musk. What's going to happen there? Well, we already know that we see significant soil erosion as it changes the nature of how the light interacts with the soil. That seems silly, but it's true. Also, we increase our local air temperature by anywhere from 3 to 4 degrees Celsius. These all seem small, and perhaps they are, but we need to just go back to the idea of how much space we need. Remember, we also need to still grow crops, and now we devote even more land to solar panels and more people. And as demand grows, we must build more of these panels. So space is the real limiting factor for solar. Let's talk about the next one, wind. All right, I'm not going to go into this. It's more complicated, but some sophisticated models from a group at Stanford have been developed, and they found that we would need 4 million wind turbines at 100 meters, industrial scale turbines. Half of these, so 2 million, would be on water, very close to land, taking up most of the coastline. The other half would cover an area equal to half the size of Alaska. Now, wind is great because you can have multi-purpose land, but think about all those wind turbines. Okay, with wind, I think the interesting thing is that meeting world demand, if we extract all of the energy we need from the wind and use it to meet the world's demand, we would extract 5% of all wind power. Not just on the surface, but all the way up to the sky. Like if we model all of the energy in the wind, we would take 5% of that. You say, well, that's not much, but it's still something. And we're talking a complicated fluid system. This would kind of be the equivalent of plugging one sprinkler on a sprinkler system. I realize that many of you might have never seen sprinklers in your life, but where I'm from, we use them all the time. And if you plug one sprinkler, the behavior of all of the other sprinklers change. So let's talk about what would happen to the weather system. Okay, I have some interesting quotes here from a few different papers. Okay, one quote from the conclusion of a paper looking at atmospheric changes due to large wind deployment. They state high levels of wind development could result in, and I quote, significant changes in atmospheric circulation. They mentioned a few specific trade winds that would possibly shift several hundred miles in any direction. We're talking about major changes in the wind patterns of the earth, resulting in large changes in where rain might fall, or where it is hot, or where it is cold. This could significantly change where it is possible to farm or live. Okay, another paper said that for large wind deployment, climate impacts, sorry about my pen again, are non-negligible. Finally, there are a few papers who disagree and say, well, we don't think it'd be that bad. But all of them tend to say, we don't actually know. Like Arrhenius, we have not predicted every consequence of large wind deployment. So, now that we've discussed the solar and wind and what happens with a large deployment of each technology, let's go and discuss my favorite topic, kind of the no-nonsense way to actually solve this potential energy crisis we have on the horizon.